Hey there. So I'm Mason Mechanica, and this is going to be my 4793 term project. I chose the topic of composite aircraft engine components. I'm an aerospace major, so this is very relevant to what I want to do in the future in terms of research and eventually a job. So before we delve into the actual composites component of this presentation, I want to do just a brief overview of the aviation industry as a whole. So the aviation industry is one of the fastest growing industries in the world with a global great growth rate of a little over 6% per year for the past few years, and global revenue just surpassed 1 trillion in terms of full aviation revenue. I mean, this is discounting the COVID pandemic. Obviously, things went down a little bit in the past year, but overall, this is a over $1 trillion industry at this point in society. And aviation has some of the highest performance requirements of any industry, particularly in engineering across the board, mainly because of just the high rigor and the high stress and the constant strain that all manufactured parts are going to be under. Now, in terms of aviation, obviously your one goal is for what you're creating to fly. You want it to be in the air. And as such, weight is one of the greatest design concerns in all of aviation and aviation engineering. And efficiency is really critical in this area because the higher your weight goes, the higher your fuel costs are going to go. And currently, fuel has quadrupled in cost over the past decade with a growth rate of about 10% per year. And fuel now comprises somewhere between 30 and 40% of all global aviation expenditures. So, reducing weight and increasing efficiency just across the board in terms of operation is one of the most critical things for the industry. So the main focus of this presentation is going to be on aircraft engines and composite applications in them. So the specific things you need to know about aircraft engines, if you didn't already know, is that they are incredibly complex pieces of machinery. They're feats of engineering beyond a lot of other things. There's tons and tons of moving components that are all under constant levels of high stress during use. They're in use under high pressure for long durations of time when the aircraft is in flight, and beyond complex shaping requirements that you can see in the internals of this engine, there's often incredibly high temperatures as the parts and the air moving through them undergo combustion in the pressurized chambers, which creates incredibly high performance requirements for any materials used in the aircraft engines themselves. Now, based on the high performance requirements I mentioned previously, this made composite use in the past, particularly prior to 2000, like the mid 90s before major composite developments had been made. This made composite use in engines very difficult. So their use was primarily in small parts across the structure. You had certain nacelle parts like thrust reversers, fairings, and cowlings that aren't under high levels of pressure or temperature that composites could be used for, especially low performance composites. But we didn't see a lot of application across the board in aircraft engines just because composites weren't able to meet the requirements. Then along came the G90 engine, which we'll speak about in more depth in a second, but this really innovated the use of composites in engines and introduced the use of RTM, resin transfer molding, into the aviation industry as a whole. So, as I mentioned previously, the innovation from GE in the GE90 engine is one of the major turning points in composite use in the aviation industry across the board. This engine and its engineering introduced resin transfer molding into aviation, introduced a lot more advanced materials, particularly in the composite sphere, into aviation. It is one of the pioneering uses of carbon fiber prepreg plies. This was like 100 ply development for a lot of the fan blades in this engine. And it even allowed for the use of composites in bypass ducts, which are an area of the engine which undergoes a high level of not only heat but pressure during use. So this was an area that was never touched by composites previously, but due to the use of carbon fiber and high performance composite materials, GE really pioneered the use of composites in this area. With the introduction of high performance composites to the aviation industry, we now see wide application across fairly all engine components in the overall design. I mean, we see carbon fiber blades, they're high use in compression and thrust reversal components, and we see the use of composites even in less glamorous things such as brackets and confining components across the board. And one of the defining characteristics of composite use has been the growth of internal manufacturing ability in engine makers. So GE and Rolls-Royce are two of the largest engine manufacturers in the world and also in the United States. And they've increased their specific composite manufacturing capability by upwards of 30 to 40% in the past decade, which just indicates not only the wide use, but their recognition of how composites are going to play a large role in the future of aviation. Now, as we've learned throughout the course of this class, there's a variety of ways that composites can be processed and made for manufacturing components. Now, when it comes to aircraft engineering, and especially aircraft engines, manual layup has been the default for a long time, even going back to the mid-90s when GE created the first major composite engine. So manual layup has been a preference because of, number one, the need for performance in aircraft engines. This limits the defects that would be present in large-scale manufacturing. And when you're creating components such as this, although production speed is a requirement, it's not as much of a factor because the performance of the components is much more important than the speed at which they're produced. So this manual pre-preg layup uses autoclave curing and has for going on 2 decades now. But this has been a little slow, as is noted for manual layup. So the development of automated processes like automated tape laying and automated fiber placement has really ramped up in the last few years, and Rolls-Royce has been a pioneer in both of these areas, and their manufacturing process has increased by tenfold in terms of composite speed. Now, RTM, which is one of the major uses, comprising I think about 30% of all composite manufacturers, is still the most widely used, but this isn't possible for certain composites such as the blade manufacturer in engines like the LEAP one seen over here to the right. So when it comes to materials used in aircraft engines, they use pretty much the variety of materials seen across the board. So fibers, you're going to see use of glass, aramid, and carbon in various applications. Glass is often used in the acoustic panels and nacelle casings and in all the cowlings. Aramids can be used in fan containment cases and often in parts of the fans themselves. But carbon fiber, especially high-strength carbon fiber, comprises about 94% of the over 12,000 metric tons used in market and is going to be the primary fiber used for the next decade in all looking forward forecasts. In terms of resins, you're going to use pretty much anything that can withstand the temperatures and pressures seen in the engines. Standard and toughened epoxies comprise a little over 93% of all matrix used in the industry, but bismaldehyde and polyamide can be used, as well as high temperature experimental substances like cyanate esters and phenolics, which use cross coupling and bonding to withstand the high temperatures seen in the internals of engines. So overall, as we've seen throughout the duration of this presentation, with the ever increasing need for efficiency and the growing market value of aviation, it's one of the highest indicators of economic growth that a country can have, and it drives GDPs across the globe. Efficiency is very important in this area. Composites can help increase efficiency in every area of aviation, but particularly in engine efficiency and weight. Looking forward, we also see that new regulations, particularly for emissions and fuel use, are going to become very prevalent in the coming years as we focus on climate change and finding new and innovative ways to deal with that. So reducing our fuel use and emissions through the application of composites in aviation are increasingly prospective developments that will help composites gain even greater foothold and continue to see use across aviation in the years to come.